Everyone, what we want to look at is a demonstration that I haven't done yet for you in class or talked about. So the demonstration is this. We have 2 meter sticks here. 1 meter stick is 1 meter long, and then I've taped 2 together to make one 2 meters long. What I'm going to do is I'm going to allow both meter sticks to drop at the same time from the same angle, and the question is who falls to the floor fastest? Is it the 1 meter stick or is it the 2 meter stick? Make your prediction now and we'll show you the results. So as we saw, the 1 meter stick hit the floor faster than the 2 meter stick, and that's all because the 2 meter stick has a larger moment of inertia. They were both experiencing torques. Yes, the larger one was experiencing a larger torque because of a bigger force. However, the moment of inertia is mr squared, or in this case, the 1/3 ml squared, because we're rotating around the pivot point, and the bigger moment definitely caused a lot longer for that thing to pick up speed and accelerate. So let's try an example here. Let's try an example for making your bike go forward. Now you push on the pedals and apply a force to the chain. That force is then attached to the sprocket back on your big wheel and provides a force of, it says 18 newtons there, and let's give that radius 7 centimeters. So let's figure out how quickly that wheel starts to spin after a couple pedals. Okay, so looking at what the information we have here, the chain's going to apply an 18 Newton force to that 7 centimeter radius. The moment of the entire wheel that's attached to that sprocket is mr squared, since it's pretty much a hoop, all the mass is on the end points. The wheel is 2.4 kilograms in mass and has a radius of 35 centimeters. And other things I know is that the wheel isn't spinning initially, and I'm going to pedal for 5 full seconds. So what we want to find is the final angular velocity of the wheel with these conditions set. So if I want to find final velocity, I know the initial, I know the time, I need the alpha. And where am I going to get the alpha? I'm going to get that from torque. So I know the moment of my wheel, I know my torque. My torque is radius times force, so that'll give me my Newton meters. Do my mr squared to get my moment of inertia, and solve for your alpha. Once you solve for your alpha, put it into your kinematics, and that should help you solve for your final omega. Doing all the numbers, pause the video, try and calculate all the numbers out. When you unpause it, the final velocity is around 21 radians per second. So that would be the rotational speed of the wheel after 5 seconds of pedaling with that force on the sprocket. Well, if that's the rotational speed, we could ask then, well, what would the linear speed be for the wheel after 5 seconds? Well, we know that the wheel is rotating at 21 radians per second, and we do know the radius of the wheel. So knowing those two things, you can actually get the straight line speed about the center of mass by just multiplying those two together. Another example I'd like to do with you is another Atwood. So at the Atwoods here, we've got forces acting on both masses, but now we said we can't ignore the pulley. The pulley has mass, the pulley has a radius, the pulley is going to rotate and spin, so we do have to account for that in our Atwood problems. So if I look at my force diagrams here, mass 1 is being accelerated by T1. So that's an easy equation to write. T1 makes M1A. If I look down at mass 2, I've got T2 and the force of gravity. T2 is less than mg, so I've got T2 up minus m2g down, and that makes mass 2 accelerate in the downward direction. And in the past, all we would do would set up the tensions and set them equal to each other, but we can't do that anymore, because if the tensions were equal, the pulley wouldn't rotate. So we have to look at the net torque, making the pulley angularly accelerate. So the net torque is pretty easy here. T1 is rotating in a positive direction, so T1 is a positive torque. T2 is trying to make it spin in the clockwise direction, so that's a negative torque. And that's going to equal the moment of our wheel. Let's say our wheel is a solid cylinder, so that's 1/2 mr squared multiplied by alpha, but the goal again, remember, is to solve for linear acceleration. So you can swap out what alpha is as a over r, linear speed multiplied by your radius. And what you get to do is we get to play some cancellation here. One radius disappears for my torque equation, and the radius on the other side goes away as well. So now I have an expression of T1 minus T2 equals 1/2 the mass of the pulley times acceleration. What do we do to solve for the total acceleration? We put T1 in here, we put T2 right there, and substitute and solve. And what you should get in the end is negative m1a plus negative 2ma plus m2g equals 1/2 ma. And this mass here is the mass of the pulley. Putting all your accelerations together, you get that m2g is the force that's making this go, and it's going to be divided by mass 1, mass 2, and half the mass of the pulley. So that's how you account for everything that is rotating and spinning when you're doing an Atwood problem. The tension is no longer equal, so you have to torque the rope on the pulley. And one other thing we pointed out today was that when you are rolling, you can look at different parts of the wheel and see how the wheel is moving. So if you look, it looks like down here, the contact point of the spinning wheel is not moving, and technically it is at rest so that the static friction can kind of push it forward. We also have the center of mass here is moving off in a straight line. Since the whole thing is rotating at the same speed, everybody rotates at omega, and it's a radius away. So that is the speed about the center of mass. If you look even higher up here, the top of the wheel is twice the radius away from the center of mass. So the top of the wheel is actually moving at 2 omega r in a straight line. So the bottom of the wheel is not moving, the center of the mass is moving at omega r, and the top of the wheel is moving twice as fast. When we focus on objects, we focus on their center of mass, and you can do V equals omega r. So that meant that when things are rolling, they have kinetic energy as well. They have rotating kinetic energy. So if objects have rotating kinetic energy, we can use 1/2 mv squared to solve for the total kinetic energy. The moment of inertia is just mass times the radius squared. And spinning objects will want to continue spinning unless they're resisted by some outside net torque. That's just the definition of rotational inertia. So another way of thinking of rotational inertia is how hard it is to shake something. When you try to shake something, that object is going to resist any change in its angular motion. So when you look for an object and you're trying to define its energies, objects may be going in a straight line, but they might also be rolling as well. So they might have linear kinetic energy, but they're also, if they're spinning, having rotational kinetic energy. So you have to account for both energies. And that's what this problem is trying to show you here. That in the past, we had an object on a hill, and we said it could turn all its potential energy into kinetic energy at the bottom and back up to the same potential at the top. However, they're showing you that at location 2, that ball is not getting back up to its highest point because now the ball is spinning. So since some of that energy is still in the rotation when it gets to height number 2, you can't actually have all the gravitational energy you used to have. So if I'd set up an energy conservation for this, down here the object has rotational kinetic energy because it is spinning, and it's moving in a straight line, so it has linear kinetic energy. Once it reaches its highest point, it looks like the linear velocity and the rotational velocity have stopped, so that means the energy can't disappear. What has happened is we've gained height, so that means we've gained gravitational potential energy. And we showed from today that we can solve for 1/2 I omega squared to give us the rotational kinetic energy, and regular kinetic energy is just 1/2 mv squared. That will turn into your gravitational energy when you reach your highest point. So we did lots of demos today with the rolling down the ramp, and we saw that objects do not always reach the bottom at the same time. It all depends on their moment of inertia, how easy it is to get that thing into motion and start that thing spinning. So the things that had smaller moments, like the solid disc versus the hoop, was able to go down the hill faster. The bowling ball is a solid mass too, so when there's more mass closer to the pivot point, those things can pick up speed much faster. And we've talked about a ton of topics in here. Table 9.2 gives you an analogous to everything we've done in linear motion to now rotational motion. So displacements in the x direction are now just thetas for our angular displacements, and so on. Torque is our equivalent for force. Moment of inertia is our equivalent for mass. Kinetic energy is almost written the same way, except for mass it's a moment, and for velocity it's angular velocity. Two things we didn't put down there were the power and work. Let's go look at those and analyze those real quick. Alright, so this is our old analogous for work. Force dotted with displacement gives us the amount of work or joules that you put into a system, how much energy you put into a system. So if I try to translate this into rotational work, rotational force is a torque, and rotational displacement is a theta. So if you look at that, we've got torque multiplied by theta, and torque by theta is also going to give me joules. We know from this, unit-wise, this is Newton meters, and Newton meters is definitely a joule. But let's look at what our torque times theta. Torque is Newton meter, but then we multiply by our theta, which is a radian, and now that there's a radian involved, since you've had that force acting through a displacement, you now have a joule. So a Newton meter for torque is not a joule until you multiply it by a radian. And if we wanted to find our power, power is just the work you do over the time it takes you to get there. So if our work is torque d theta, and I'm going to divide that by time, remember that d theta dt is omega. So really, a torque times an omega will also get you the amount of power that is generated, just like force times velocity. And if you look at that unit-wise, Newton meters multiplied by radian per second. The Newton meter radian is a joule divided by the seconds, so you still get the watts of power that we're used to generating. So if they ask you questions like that, yes, you can solve for power and work using rotational equations. So if I was going to try and solve for the speed of a solid sphere, so a bowling ball rolling down a hill, I would use conservation of energy. Conservation of energy is going to say that at the beginning I have gravitational energy. By the time the ball gets to the bottom of the hill, it's going to be moving in a straight line, but the ball's also going to rotate. So it's going to have an omega and a velocity. So that means it's got rotational kinetic energy plus linear tangential kinetic energy. So you want to set that up, do mgh equal to 1/2 I omega squared plus 1/2 mv squared. And if I want to solve for the speed at the bottom to prove that the speed is faster than other rotating things at the bottom of the hill, I'm going to sub in my moment of inertia, and I'm going to get rid of my omega and make my omega straight line linear velocity. Putting in the moment of inertia as 2/5 mr squared and subbing out omega to be v squared over r squared, I can see that some things will cancel for me. The things that will cancel right off the bat is the 2's, the r squareds, and so I'm left with 1/5 mv squared plus 1/2 mv squared. So 1/2 plus 1/5 ends up giving you about 7/10 mv squared. Getting rid of the mass again and solving for v gives you the square root of 10/7 gh. So that's the speed of a bowling ball heading down the ramp while it's rotating and moving in a straight line.